Aloha, acid and base students. This is our 12th and final video in the series. If you made it this far, then well done. This is a summary video and we'll discuss how to classify solutions. If you have a solution that you're interested in and you want to classify it into one of these categories, in other words, you want to know what type of solution it is and perhaps what is the pH. Well, it depends. If someone gives you an actual beaker containing this solution, but they don't tell you anything else, then you're going to have to go into the laboratory to answer these questions and to put it into the appropriate category. And given only the solution itself, you'll probably be doing an experimental titration using a pH meter. So this method with that tool will help you put it into the appropriate category and allow you to determine the pH as well. If you don't have the solution itself, but you're given the chemical composition, in other words, you're told what the molarity is and what the chemical is, a certain molarity of a certain chemical, then you can sit at your desk and answer the question using the methods that we've discussed in this series. So here are the categories. There are 5 of them. Maybe it's a strong acid, maybe it's a weak base, maybe it's even neutral. If you're given the molarity and chemical identity, you should be able to classify it and even calculate the pH. So first, strong acids. These we dealt with earliest in the series, and they were pretty simple. They're easy to identify because there's only 6 of them. HCl, HBr, HI, and these 3 oxyacids. Now this one right here, sulfuric acid, we did not do a problem where we calculated its pH. So if you have sulfuric acid, you can classify it as a strong acid, but we didn't discuss, or we didn't do a problem where we actually calculated the pH, but we did a similar problem where we calculated the pH of another triprotic acid, phosphoric acid, and you can go back and look at the video for polyprotic acids, and you would follow a method similar to calculate the pH for sulfuric acid. It requires a little special care, but I think you can do it. So strong acids are easy to identify because there's just 6 of them, and you've memorized this list if you're a good student. Strong acids undergo full dissociation. So if you take HI, for instance, Hawaii's state chemical, so HI is hydroiodic acid, it will dissociate fully as acknowledged by the one-way arrow, and all of the HI molecules will turn into protons. All of them will split apart. So the initial acid concentration will be the equilibrium proton concentration. So if you're told the molarity of the initial acid, that's going to be the molarity of the proton, and you can plug that into the pH equation to quickly calculate pH. So strong acids are easy to classify, and they're easy to calculate the pH for. Weak acids, there are many more of those. You know you have a weak acid if you can find its Ka. If there's a Ka, that means it's a weak acid. Now, you might not be able to find the Ka for your weak acid, but if its conjugate base has a Kb, then you can use Ka times Kb equals Kw to calculate the Ka of your acid. So the conjugate weak pairs videos discusses how to do that. So there are many weak acids. They all have Kas, and I've listed several of them right here. HF, for example. Weak acids undergo partial dissociation, so HF will produce protons, but it's an equilibrium that occurs between the reactants and products as acknowledged by the equilibrium arrows here. Now in this case, most of the acid will be undissociated. You'll only generate a little bit of proton concentration, so the initial acid concentration will be much greater than the equilibrium proton concentration, and to figure out what the equilibrium proton concentration is, you need to use the ice table and solve for x. So do that and then get the proton concentration that way and then the pH. So it takes a little work to get the proton concentration for a weak acid system, but once you do, then you can find the pH. So there are lots more weak acids. We even discussed some metal cations that complex with water, which can act as weak acids as well. You can look up the metal cations as weak acids video if you want to recall that. Now, neutral solutions are, or maybe these are the ones you're hoping for because they're the simplest. Neutral solutions such as sodium chloride, potassium bromide, magnesium nitrate. Well, when you have when you're told what the chemical is and what the concentration is, if it's something like this, you have to consider the cation and the anion. So, cations are neutral if they're, alkali and alkaline earth metal cations. It's only highly charged metal cations which are acidic. If you have a metal cation, but it's not highly charged, then it's going to be a neutral cation. And if you're dealing with an alkali or alkaline earth metal cation, then those are all neutral. Those are metal cations. There are other cations that can be acidic, but those are the conjugate acids of weak bases. Like ammonia, is NH3, and if you give it a proton, it turns into NH4+. That's a cation, and that's a weak acid. But if it's a metal cation, it's only acidic if it's got a really high charge on it. So alkali and alkaline earth metal cations are +1 and +2 charges. Those are not acidic. The anions here are all neutral, and you should be able to identify these as the conjugate base anions of the strong acids. This is chloride, which comes from hydrochloric acid, bromide from hydrobromic acid, and nitrate from nitric acid. So those are all strong acids, so that means these are all neutral anions. So the conjugate bases of strong acids are neutral. So you should know what neutral metal cations are and what neutral anions are. So there are 5 anions that are neutral. And, when we talked about the strong versus weak acids, we went into those, 5 neutral anions. So weak bases, these are like weak acids. Now there are many weak bases, and it's a weak base if there is a Kb. If you can find a Kb, then that means you have a weak base. Sometimes you can't find the Kb, but you can find the Ka of its conjugate acid. So like F-, for example, you probably won't find a Kb for F-, but you can find the Ka for its conjugate acid HF. And hypochlorite, ClO-, you won't be able to find its Kb, but you can find the Ka of its conjugate. And then if you know the Ka of its conjugate, then you can use Ka times Kb equals Kw. You can use that equation to calculate this Kb. So here's just a few weak acids. Weak acids generate a little bit of hydroxide concentration. So take ammonia, for example. It undergoes a partial dissociation to generate some hydroxides and some ammonium conjugate base, conjugate acid cations. In this case, most of the ammonia is undissociated, and the initial base concentration is a lot bigger than the small amount of hydroxide that you generate. So you have to use an ice table here to find the hydroxide concentration. And once you do, calculate the pOH and then the pH. So weak bases, involves using an ice table to find hydroxide, then get the pOH, and then the pH. Weak acids use an ice table to find the proton concentration, and then the pH. So weak systems involve ice tables in your calculations. Strong bases, these are pretty easy to deal with, like strong acids are. Strong bases are soluble metal hydroxides. So these are your alkali or alkaline earth metal hydroxides. For example, lithium hydroxide, sodium hydroxide are just a few strong bases. Strontium hydroxide can give you 2 hydroxides per formula unit. So there are, a handful of strong bases. Most hydroxides are insoluble, but if you know what the soluble ones are, those are the soluble metal hydroxides. Those are the strong bases. There's like 7 or 8 of them or something. So these will fully dissociate in water, like potassium hydroxide will produce, all of it will produce potassium ions and hydroxide anions. So if you know what the molarity of your potassium hydroxide is, you immediately know what the molarity of your hydroxide is. And so since the initial base concentration equals the hydroxide concentration, you know what this is, and you can calculate the pOH and then the pH. If you have something like strontium hydroxide, then it's going to be twice the initial base concentration equals the hydroxide concentration. That's because you get 2 hydroxides per formula unit. But still, for strong bases, it's easy to get the hydroxide concentration and then get the pOH and then the pH. So that's the general strategy. If you're given the chemical composition, depending on the type of solution you have, you should know how to classify the solution. And then once you classify the solution correctly, figure out how to calculate its pH. Okay, the method for getting the pH is different depending on what type of solution it is. And in the first method, which involves taking your solution and going into the laboratory, we'll discuss titrations in the next series. So tune into that, and aloha.